You're listening to Climate Now. I'm James Lawler.
And I'm Catherine Gorman. You've heard about it in the news. Under President Biden's new infrastructure bill, the U.S. is investing billions of dollars in roads, bridges, passenger rail, and charging stations for electric vehicles.
And with that, it's more timely than ever to kick off our mini-series here at Climate Now, all about transportation. For the next several episodes, we'll be talking about road transport, maritime transport, and aviation, starting with today's episode on electric vehicles.
The transportation series will be guest hosted by Darren Howe, Senior Charging Manager at Cruise and a former Tesla applications engineer.
Hi, Darren.
Hi, James.
About a year ago, I was introduced to Darren Howe, who at the time was working at Schmidt Futures. I reached out to Darren because Darren was connected to a variety of people who are active in the climate space and energy transition space. And we started talking then, and Darren has since moved on, and he'll tell you about where he is in a moment. But we crossed paths again because I saw that Darren was writing a fascinating blog on Medium called Catalyst Climate, all about road transport and decarbonizing road transport. And I thought, this would be a really great topic for a focused series for Climate Now. So Darren and I started talking about doing this together, and I want, maybe Darren, you could introduce yourself, tell folks who you are.
Yeah, certainly, James. Well, back when we met at Schmidt Futures, I was there working on climate-related initiatives for Schmidt Futures. But actually, my background is more in the operating role. I started my career in the solar industry, working on what is known colloquially as module-level power electronics. And then from there, went to Tesla, working on EV charging infrastructure, kind of designing the optimal systems. And now I work at Cruise, the autonomous vehicle company. What's interesting about Cruise is they operate an all-electric fleet, and that gives us a really interesting lever in terms of charging and energy infrastructure.
Amazing. And we're going to be talking more about autonomous vehicles, AV fleets during this series. So let's do it.
Let's do it. Hi, Andy. I think we could take this opportunity to dive a bit into your background. Could you tell us a little bit more about your background? I know you've had some very interesting experiences before.
For sure, yeah. So I have always been interested in sustainability, even going back to high school, and went to college with the intention of studying environmental science and ended up majoring in geology. And so decided to first spend a few years working in the policy world. So right after college, I spent about 4 years working on climate change policy, a couple of years in Hong Kong and then a couple of years in Washington, D.C. I think like a lot of people who worked in DC got a bit frustrated with the pace of change and my ability to impact things. And so decided to go back to grad school and try to shift over to the private sector side of sustainability. When I was in grad school out at Stanford, I got really excited about Tesla. I felt that one of the problems in DC was that everybody in this environmental community was very insular and kind of talking to each other and working on these problems together, but not really reaching outside of that community very much. And I felt that was very important for advancing sustainability. And I thought Tesla was unique among the companies out there that they actually resonated with people who had, very little interest in sustainability. And I thought in advancing the cause, that was going to be a critical thing going forward. So after grad school, I spent a few years working at Tesla and then jumped into starting a company called Redwood Materials that became a major player in battery recycling over the last couple of years, and transitioned out of that company at the end of last year, and kind of have spent the last few months just exploring new ways to have an impact and a few new startup ideas and other projects.
Yeah, you described how you went from DC back into grad school and a little bit about how you chose Tesla out of grad school. But what was it that made you decide that Redwood Materials was a really interesting opportunity and impactful one?
Yeah, I think it's a problem that had always been coming up. When I was working at Tesla, we still were getting a lot of questions from the media and other people in the ecosystem about the sustainability of the products. There was a narrative out there that, hey, we're using oil to run these internal combustion engine vehicles. Now we're going to use lithium and nickel and cobalt, and that's all going to need to be mined. And oh, by the way, we're powering it with coal. In a lot of places, is this really more sustainable at the end of the day than a gas vehicle? And that narrative was still kind of in the background. Recycling was often a part of that. Hey, you're creating this product and you're going to have a massive amount of batteries. What's going to be done with them at the end of life? Is it just going to be contributing to this electronic waste problem that already exists in the world. I think the other thing that was really interesting to us was taking a look at the comparison between how sophisticated and automated the Tesla manufacturing plant was, and then going to some of the recycling vendors and seeing what they were doing with the products that we were sending them. And it's kind of amazing to see that contrast between the super sophisticated, automated, robotic manufacturing and kind of like a scrapyard where there was no new technology beyond like a big blade cutting a piece of metal. And so, I think both of us felt this strong sense that, hey, this is a problem that's going to need to be solved for EVs to be sustainable.
So would love to segue into sort of setting the stage for our audience in terms of the trends in the electric transportation sector.
It's still a relatively small percentage of the overall vehicle market. I think it's in the sort of low single digits of penetration in terms of vehicle sales. And most of the projections I've seen are looking at that going up to tens of percent, maybe around 30% or next 1 to 2 decades. So it's steady ramp up from low to mid teens of percentages of new vehicle sales.
Mm-hmm. And what about battery design and materials? What are sort of the key trends to understand?
There's a few important ones. So the thing I feel right now about battery materials and battery design is it's kind of a period of uncertainty. There was sort of an initial period of time with batteries where they were only made by a few companies, mostly in Asia. And there was not a lot of broader knowledge about how to make them. Then the original Tesla Gigafactory was built in Nevada. And it kind of started this last 7-year or so period where the knowledge about the chemistry of batteries and how to make batteries became a topic that got disseminated much more broadly among scientists, engineers. A lot more research funding went into it. A lot more large corporates started putting a lot more research dollars into it. And I think what we're seeing right now is kind of the first wave of the innovations that have come out of that. And so there's innovations across all different aspects of the battery. There's, cathode materials, the anode materials, the manufacturing processes, the sort of mechanical structure and size. And so I think we've kind of come from this period where there was only a little bit of knowledge to one where it's kind of, exploded across many different avenues. And then I think over the next couple of years, you might see a little bit of like seeing which ones of those are going to come out as the winners and the losers. We're sort of right in the middle of this burst of different ideas. Just to provide a few specifics, solid state batteries are sort of one that's a big focus for several companies that's getting a lot of funding and trying to commercialize. And then there's anode materials like silicon anodes that other companies are trying to commercialize. So there's a few different kind of major trends like that. But one thing to think about is these could all be put together in some way. It's like all of these different components that people are working on that might all be able to be sort of mixed together at the end of the day.
But you trace this explosion of innovation to that Tesla factory, right? Like it really took that major investment. And when was that?
I think in the summer of 2014 was when they started the construction.
Yeah.
It was the first major lithium ion battery factory outside of Asia, as far as I'm aware. And to me, it feels like that really kickstarted this intense activity. I mean, alongside kind of the growth of Tesla, I think those were kind of like Tesla making everyone feel that EVs were going to happen, along with this kind of greater dissemination of knowledge and interest in lithium ion batteries.
Has Redwood now successfully commercialized that process of taking end-of-life batteries and converting them into reusable raw materials for battery production or other production?
I don't know yet if they can say for sure that all of the raw materials that are being produced are going into batteries. I don't think the supply chain at this point is quite organized in a way that could support that claim, but that's certainly their intention. And with some of the recent announcements with Ford and other companies, it's clear that if that's not they, certainly in the future, it seems to be something that they're moving towards with some of these customers.
Great.
You kind of alluded to this already, Andy, but this is a great segue to a question that we had around how these differing chemistries affect recycling? Are there impacts behind industry shift towards specific chemistries such as LFP?
Yes, I think there definitely will be. And it may give some advantage to recycling companies that have a more robust and more flexible process that can deal with different chemistries or have the ability to sort them out on the front end. So they're not putting the same ones into the same process if they're not compatible with each other. I think you probably will see two major processes developing. If LFP is really going to become a major chemistry, you'll probably see a LFP specific process and then a sort of nickel-based cathode specific process. But I think there will be companies that have different processes for the different types of cathode materials.
That seems quite complex, right? You can't just use a standard process and say, hey, this is going to work for everything. It almost seems like you need an escape hatch for whichever chemistry is coming in. Do you see that as fundamentally limiting for the recycling industry, or do you think this is a solvable problem?
I think it's a solvable problem. I think maybe it's very difficult when you're getting batteries in to know, hey, is this like NMC 811 or a 622? Telling it that level of granularity, or like how much silicon percentage is in the anode of this battery. But I think telling which ones are LFP and which ones are not LFP is probably something that companies can figure out how to do over time, just based on educating their suppliers of how to sort them out better. I feel like it's a solvable problem. I think the more challenging long-term problem with any recycling business is that manufacturers are always trying to reduce cost and design out expensive materials and components of their products. And the returns that are available to recyclers are almost always based on the raw materials value in the original product. And so, you see in a lot of recycling industries over time, the value that's available continues to decline because manufacturers are trying to reduce their bill of materials cost. And I think that's kind of part of what's driving the shift to LFP. And so, that's going to be a challenge for the industry in the long term, is sort of how to deal with the lower amount of value that they're able to extract from the materials.
Yeah, that's such an interesting insight from someone who, it seems obvious for someone who's in the industry, but people who are not in the know, it's not something you would really think about.
Yeah, and I think over time too, you see products becoming more complex as well, and that's always a challenge for recyclers as well.
So Andy, I think related to that answer, I wonder if you could talk about what drives, battery design innovation right now. Is it cost? Is it range? And to what degree are those considerations driving the current choice of preferred chemistries today? I don't know that everyone will know what LFP is, for example. So maybe you could sort of define some of these technologies as well.
LFP is a type of cathode material. It's an iron-based cathode material. And then the other major group are sort of the nickel-based cathode materials. And LFP has been getting a lot of attention, even just in the last few months. People are moving towards it because it is lower cost, because the materials are more abundant. Iron is much more abundant on Earth than nickel and cobalt. And that's obviously related to cost. If something is more abundant, it's going to be likely lower cost. And then there's a few other factors that are driving in that direction, like lifetime. People talk about a 1,000,000-mile battery, which seems more possible with LFP because of some of the technical characteristics. And then they also talk about LFP being safer, less of a risk from a hazardous standpoint. And so those are the main things that are driving in that direction. And on the other side, with kind of the nickel-based ones, you have basically a higher energy density, which is the amount of energy you're able to extract from a certain weight or volume of a battery. And, that's still extremely important in some applications, but it's starting to get to the point where, the range of a battery is getting to be good enough for a lot of applications. And so for passenger vehicles, I think that's why you're seeing a shift to the LFP batteries, because it's maybe a little bit worse on range, but it's better on cost and these other characteristics.
Hmm.
And so that's why you're seeing a shift in that direction.
Can I add a bit of color here, actually, James?
Oh, yeah.
Yeah, this is a really interesting topic. So as Andy mentioned, LFP does have lower gravimetric and volumetric energy density, but that's where we're seeing people who actually think about systems design really leverage the advantages of that. So even though volumetrically it's less energy dense than some of the nickel-based chemistries, if you have innovations like cell to pack architectures, then you can actually increase the volumetric energy density on the pack level as opposed to the cell level.
And talk about what you mean by that, Darren. What does that mean for those who may not have heard those terms?
Yeah. So gravimetric energy density is basically how many kilowatt hours you have per kilogram. So it's based on mass. And then volumetric is per liter. So both of those matter for electric vehicles because you don't want to be driving something really big, even if it's really light. This is the problem with hydrogen. But in terms of cell to pack, that's an architecture which I think really came to public consciousness at Tesla's battery day, where they wanted to create the 4680 cells, put it as a structural element within the cell, within the pack itself, instead of encasing it in a module with a bunch of extra packaging. So one of the interesting innovations that have come out recently is BYD, a major Chinese EV manufacturer, coming up with their Blade battery. It's a cell to pack architecture. And there were a set of researchers from Penn State University that basically said, hey, one of the weaknesses of LFP is that it doesn't work so well at cold temperatures. But because you have this cell to pack architecture, if you just heated that pack regularly and made it consistent, then you actually still get a huge volumetric energy density boost on the pack level. So thinking from a systems perspective is really valuable in this industry.
Really cool. Interesting. Yeah, there's so many factors that are not necessarily immediately obvious when you start to delve into batteries.
Yeah.
So I wonder if we could just sort of take a bit of a step up in terms of the waste that comes out of battery electric vehicles in general across the life cycle. I wonder, Andy, if you could just talk about the full cycle and all of the waste that is produced from the mining to production, manufacturing to use and end of life.
Yeah. So, starting at the mine, when you're processing an ore material, the metal or material that you're targeting is a very, very small percentage by mass of that original ore material. So typically that whole thing goes through a kind of a mechanical size reduction process, and then several different types of separation processes to concentrate the metal that you're targeting at a percentage that's higher than it is in the original ore. And, basically every step of that process has some level of waste of, material being removed that is not what you were targeting. Depending on how those processes take place, if they're just pure mechanical processes, the waste is probably just basically the same stuff you took out of the ground. It's just the rock that you didn't really want in the first place. And so it's not necessarily very different. But some of those processes start to involve more chemicals and more chemistry. And so you get some types of waste that have a little bit of a material in there that wasn't present in the original. And so, that's kind of the story of the mining phase. And then from there, you sort of go into various steps of further refining that and making it into an actual product. And basically, if you go into any factory or look at any sort of manufacturing process, you're typically going to have several percent yield loss at pretty much every step of the process. It's very difficult to have any step of the process be 100% yield with the quality that you need. So, in every step of making a battery cell and making a battery pack, there's going to be a few percent that is not fit to move on to the next phase. And so then that all gets sort of pulled out and goes into a recycling stream.
Can you talk about some of the numbers there? Like when you say a few percent, how big is this problem?
I can't get into any sort of proprietary numbers. I think that's a very guarded secret, but I think the Argonne National Lab model uses estimates between kind of 90 and 95% yield for most of the steps in the process of battery cell manufacturing. So it is a bit of a compounding thing. From my perspective, it's having worked a bit in manufacturing, and I'm sure folks would know more about this than I do, but it's almost an inevitable part of any sort of high precision manufacturing process that you're going to have some yield loss, either from a phase when you're starting up the equipment, or maybe something breaks or something isn't working properly. It's just almost, to me, a feature that's going to be very, very difficult to design out. Maybe if, we achieve the future of, making everything 100% of the time, like that won't be the case. But to me, that waste can be reduced, but not eliminated. It's just not possible in a high precision manufacturing process.
And then I guess moving to end of life.
So then you've got that coming out of the factory. The good thing about that is those streams are generally fairly consistent. And so it's easy for recyclers to actually process those because they know it's going to be pretty much like a certain volume over a certain period of time with a certain composition. So it's actually a pretty easy one. It's kind of the low-hanging fruit for the recycling companies to process. And a lot of that makes its way pretty easily back into the supply chain. When the products actually get made and get out on the road or in the real world, that's when you get a lot of the complexity. And so, there is a certain amount of scrap generated over the life of any product. And often that is warranty replacements. So things that just fail, a part fails and it needs to be scrapped. In the case of vehicles, obviously you have accidents or wrecks that people get in. And so basically, from the point a class of vehicles hits the road, every year there's a certain percentage that don't progress and they actually go to scrap. And so those are ones that are coming back kind of in the middle of the life of a vehicle. I don't have hard numbers on that either, but I think it's again in the kind of low single digit percentages of vehicles per year in that group. And then, after that's kind of like the on-road scrap. And then at the end of the day, there's also the sort of true end-of-life scrap where a battery or a vehicle may have reached the end of its true useful life and then need to be either put into a second use or recycled back into raw materials. And I think for the battery recycling market, that's still, a pretty small percentage of the vehicles that are getting recycled are the ones that are sort of true end of life. There's some of the early models like the Nissan Leaf that are reaching that stage, but not very many Tesla vehicles, thankfully, are kind of yet getting to that true end of life phase. And so that's going to be a growing sort of stream over time.
It sort of seems from a ignorant perspective that with an internal combustion vehicle, end of life is probably roughly similar depending like for all the different parts of that piece of machinery versus a battery electric vehicle where you could imagine the battery having a very different end of life profile from the rest of the vehicle. Is that the case? What will fail first in Teslas, the battery or everything else? Or is that even an interesting question?
I think it is an interesting one. And honestly, I'm not sure if we really know yet. I think it's still pretty early days in terms of, battery health analysis and characterization and innovation that's extending the life of batteries. And so, I think it's actually not easy to answer that yet because people don't necessarily know how long the useful life of these batteries really will be. I think the initial Tesla warranties were 8 years, but to provide some completely anecdotal evidence, my wife's parents have a Tesla that I think they got in 2013 or around that time, and still has well over 200 miles of range in the battery. And the fact that it's maybe now only at 80% or so of the battery capacity that was when they bought it, doesn't really seem to faze them too much, and they're perfectly happy to keep driving it for a number of additional years. So I think, in my view, I think the batteries are going to last longer than a lot of people maybe are expecting.
This is a great segue to the next question here. How do you think about second life applications versus second use, battery electric vehicle markets versus just recycling? Yeah, how do these three use cases interact with each other?
Yeah, in my view, the second use and the type of recycling that Redwood is doing are very complementary. Because generally what you see in some similar spaces like electronics recycling are that there's one group of companies that pops up to do kind of the refurbishment and putting the batteries, or in that case, it's circuit boards or computers, into a second life application. And then those companies have a certain amount of products or devices that they are not able to be repurposed. They fail for whatever reason, and those get sent on to recycling companies that do the material processing. And to me, that's a pretty efficient way for this industry to develop as well, is that there'll be a certain group of companies that pop up over time that work on figuring out which batteries can be reused and repurposed into certain applications. And then there's going to be a certain amount that they determine can't be reused, and those will get sent to recycling companies. So I think ultimately, to me, these are very complementary industries that will both exist in the future. Likely, the repurposing will be a smaller but higher margin, and the sort of material processing will be a larger volume but likely lower margin business. And companies will specialize in one or the other, depending on kind of what their appetite is for those types of business.
So it sounds like you don't have a strong opinion about whether second life batteries for stationary storage, for instance, is a good or bad idea.
Yeah, I see a lot of the challenges of it, to be totally honest. I spent a little bit of time working in the power generation business for a couple of years, or didn't own, but I managed a small hydropower project in the rural northern part of California. And we had a contract to sell wholesale power to PG&E. And I think that it's very hard to make money in the wholesale power market because the price of wind and solar generation is coming down so much. And there's so many other innovations that are happening in the market that are essentially driving down the price of wholesale electricity. And the value of stationary storage, I think, is very uncertain in my view, that you're competing against a lot of other ways that these renewable resources could be balanced, greater grid integration, things like that. So I think that's slightly my personal bias of some of the scars of working in this wholesale power business. But if I were starting a second life battery company, I would most likely focus on mobility applications rather than trying to compete in a very competitive wholesale power market.
Not knowing too much about Redwood, but recycling companies, is the sweet spot there, like taking used product, taking end of life product, or taking sort of waste product to raw materials for other supply chains? Or could you imagine like a more vertically integrated recycling company that did, as you just suggested, sort of taking vehicles and actually creating new vehicles for other purposes?
I think they're pretty different disciplines. The sort of recycling and refining business is much more of a sort of chemical engineering business, and the other one is more of, I guess, electrical and mechanical engineering. And
Right.
there's certainly some people who can play in both areas. As you've seen with Redwood and some of the other recycling companies, they're actually vertically integrating in the other direction. So they're looking into make, cathode materials themselves or anode materials themselves, which I think is a more complementary business based on their capabilities than kind of making the different types of second life products.
So Andy, you had just talked about sort of the different architectures that are coming in. We touched upon cell to pack. How do innovations like that affect recycling operators?
I think it's a real challenge. Mechanical disassembly of the vehicles. I think if you go to a conventional automotive recycling facility, you see they have these very, very large shredding machines, which is basically the only way they can deal with a sort of whole vehicle and actually process it back into commodity materials, because you can't manually disassemble a whole vehicle chassis unless you have like a big oxyacetylene torch or something like that. And I think the more that the battery pack becomes essentially part of the chassis of the vehicle, integrated in that way, it's going to require essentially like a large scale shredding process to be the sort of front end of a lot of these recycling processes. And I think that's certainly possible, but it just maybe removes a little bit more, flexibility from the recycling companies to have other ways of processing them.
And that's where all the trends in the electric vehicle market would point toward that architecture, like a more integrated battery pack with the vehicle rather than a battery that can be taken off more easily.
It seems like there's some of the manufacturers are going in that direction. You also see other companies that are working still on kind of the battery swap architecture. They're mostly more like smaller companies that are kind of starting to go back in that direction. But I think at least the major OEMs have mostly indicated that they're going to the sort of cell to pack. Of course, they may mean slightly different things by that, and perhaps there will be ways to remove cells or remove components without mechanical shredding. But I think that's kind of the direction that recycling will probably head if you can't remove the battery pack from the chassis of the vehicle.
Andy, why don't you tell us like what you're interested in now that you've left Redwood Materials?
Yeah. So I've been spending time researching a lot of different areas of the clean tech industry, and both within the battery and EV space, and then a little bit outside of that. As I mentioned before, I think my conclusion about the battery cell technology is we're in an era where it's just so many different ideas out there that I'm finding a hard time sort of narrowing in on which one I want to bet on as sort of the next big sort of battery cell technology. So kind of what I've gotten the most interested in is different applications within the EV space, and which one of those is kind of on the verge of becoming commercially viable next. And I really feel that, commercial vehicle electrification and heavy duty trucks are sort of the next big phase of electrification. And this isn't just my insight. There's a ton of people working on this in various different aspects, but it feels like the battery technology has reached a point where it can enable a lot of these commercial use cases without major advances.
That was really, really great, Andy. Really fascinating. Great perspective on everything in this area. So thank you so much for your time.
Yeah.
It's been great having you on, Andy.
Yeah, thank you guys.
So I always really like to talk to people who know a lot about sort of areas of the economy that I've really never thought about. So all of the sort of opportunities for recycling and sort of the size of that need at different sort of stages of production, and thinking about how that works and what the sort of downstream opportunities for those products or for the outputs of that recycling process can be are really fascinating. And then to map that onto an industry which is in such tremendous flux right now, where it's not clear what the supply chain looks like or what the output of the process looks like, is just sort of a very exciting thing to contemplate. And I thought it was interesting to hear where he has focused his attention so far, and now, where he's looking. I thought one other thing I thought was very interesting was, now that he's past Redwood and he's looking back at the EV space and thinking, oh my gosh, there's just even too much to even sort of there's so much happening now that he's now looking forward, and trucking is kind of the next frontier. I thought that was also an interesting insight. What about you?
Well, this industry definitely seems like they're trying to assemble the plane as everything is changing around them, right? So it's fascinating to be part of that. And I guess my own 2 cents is that as someone who's worked in solar and EV charging, it's very exciting to see infrastructure, a traditionally non-sexy thing, become extremely exciting right now. I think there was one interesting piece that we didn't necessarily touch on as much on the LFP and the chemistries. Some interesting context there is just the geopolitics of it all as well, right? Mm-hmm. So what Redwood is doing and what other recyclers are doing are kind of complementing new mining efforts to obtain minerals for both, the US, Europe, China, and the ability to kind of leverage recycling as a way to almost have a domestic supply chain is really valuable.
Yeah. And I guess it wasn't fully clear to me, how real is that today? Like, if you are trying to produce, LFP batteries, let's say, can you sign a contract with Redwood today for a supply of, like, metal?
Well, it sounds like, I'm certainly not part of the company, but it sounds like that is more of an aspiration, based on what Andy was hinting. And my sense, he didn't explicitly say this here, but my sense is right now there are some pretty big needs even from the scrap side of things, and that because not a lot of cars have actually reached end of life, that's more of a looming need, but probably not something that is happening today.
Right.
Another interesting point about LFP is, I don't know if you're aware of this, there's a really weird quirk. So like, why has LFP suddenly come into its own in the industry? That chemistry was invented in 1996 at the University of Texas. And I don't know all the details, but they applied for a variety of patents. But when China was coming up, they actually granted China the ability to license this technology free of royalties, as long as they didn't sell it outside of China. So yeah, so that may have been one of the reasons why LFP has really gone down this cost curve. And what's interesting is now that those patents are actually set to expire in the next few years, I think a lot of OEMs are looking at that chemistry and saying, hey, now we can use this chemistry without infringing on patents.
Oh, interesting. Oh, that's fascinating. Yeah, we didn't cover that.
No, there's just so much. We could have an
Yeah.
hours long conversation about this.
Yeah. All right. Well, thanks. That was great.
Yeah, this is fun.
That is it for this episode of Climate Now. To watch our videos and listen to other conversations, visit www.climatenow.com, where you can also sign up for our newsletter to be the first to know about new releases. Thanks so much, and hope you can join us for our next conversation.